I have a little example that I've created for you just to highlight some of the differences here between that perf counter clock and the time.time. And as I explained before, time.time is based on an actual, my system's date time. And so what you can see here, just a couple printouts, and then we're going to get my data frame. And in this data frame, you can see that I have 3 columns as a hierarchical or a multi-index column. And I have my raw datetime.now, and I have my deltas. So the deltas is essentially, row 2 subtract away row 1. And when I perform that for my datetime.now, you see that I get 0 days. And for my perf counter, you can see that I get a delta of 1. And so you can see that this is about 1 second. Every row, every measurement that I took about 1 second. And so what we can do with this is we can actually bump this up. And I'll want to just sleep a little bit longer here and give that another run. Maybe I'll just want to grab some more measurements as well. But this script is actually changing my system's clock. It's changing the date time that's associated on my machine. And so you can see that I'm stopping my network sync up for my clock. And then here I'm actually manually setting my date time. And then I'm sleeping because I want my Python process to actually start running and collecting data using that datetime.now. And then I'll set the time again, and then sleep again, and then just restore my system to its original state, re-enabling some of these parameters. This will be running in the background while I'm actually collecting my data here. And you can see here that all I'm doing is I'm collecting a measurement from now, which uses datetime.now, it uses time, and it uses perf counter. And you can see that I'm appending those to a list and I'm sleeping. And I'm trying to get these two things to overlap where I end up grabbing a datetime.now once that previous shell script you saw has changed my computer's date time. And what you can see here is on this very first row, if I look at the datetime.now for row 0 and row 1, we actually see a slight shift by 1 second, but backwards, And so when I calculate the delta, I'm seeing, oh, yeah, it's a whole day behind, but then add 23 hours. So it looks like this timing between these two measurements, there's actually a negative interval, which absolutely doesn't make any sense at all, because if I measure something right now, and then I measure it again and I take the difference, time, at least in my reality, only moves forward. And so that's what this perf counter is all about. That's what the monotonic clock is all about. It's all about implementing clocks that only move forward, and therefore will actually have meaningful results every single time that we want to measure it. So if you're ever implementing a timer in Python, I would strongly urge you to use perf counter or to use monotonic. Perf counter on most machines will have a higher tick rate, I should say. So it's really good at measuring kind of very small gaps of time, whereas monotonic's a little bit larger or smaller of a tick rate. But the thing that I want to impart with you with this example is when you are taking timings, it is actually quite nice to capture both the delta in terms of the perf counter, and it's actually quite nice to capture the raw date time now, because with the perf counter you can't tell when something was called, when an event happened, but I can do that with the datetime.now. And so having just both of these pieces of information, if you're logging them, is actually quite nice to have, because it will let you go back and perform an investigation or perform correct guidance checks. So taking a look at all those clocks that we were just talking about, you can see that we have many, We have our time, we have our monotonic, our perf counter, our process time, and you can see that these clocks all have different attributes. This is at the Python, API level, so there's just kind of some summaries of these that are exposed to us. But you can see, is this clock a monotonic clock, meaning it's only going forward? Is this clock adjustable, which is very important, Can this clock actually slip from underneath us or change from underneath us? And you can see here for the time.time, that's actually true. Now the interesting part is the resolution for all these is the same. And so we might think that the performance clock might be the same as the monotonic clock in this case, but it really does depend on your machine that you're running this on. But in all cases, I would recommend using perf counter over monotonic. That's all for instrumentation. Let's talk about development. What if we need just a little bit more granularity into our timings, For instrumentation, it was all about timing maybe the execution of a Python function or the execution of a block of code. What if I want to look a little deeper? And if we do want to look deeper, if we want to actually time every single function call, well, we can use that set profile approach that I just shared with you, but we can also use something like cprofile, or we can use something like timeit. Now, these are two slightly different tools, so I'm not going to say that they serve the same purpose, but I'll show you what timeit's all about. Timeit is all about running a program, running Python code, I should say, and then measuring how long it took to actually execute that Python code. You can call this at the module level, so from the command line, or you can actually also call this from within a Python program. You'll just need to pass a couple of arguments. It'll look something kind of like this. So you just go ahead and import timeit, and then you pass it an arbitrary expression. This is served as a string. So if you have functions in here, if I wanted to say define A, and then I'll sleep, and within A, I'll sleep for half a second. Well, let's take a look at this. We'll just print out this timing of just 1 + 1, just to make sure this works before we get to a little bit more contrived of an example. So we can see that this works. It doesn't take very long. It takes 0.02 seconds, which it's a little slower than I would anticipate, but we can actually do something like this, time the execution of A. All we need to do is we need to pass timeit right these globals. And so timeit has its own namespace, it's starting up its own process, and then it's actually executing this code for us. And I believe that's number. Yes, number equals 1. The neat thing about timeit is by default, it will actually run things multiple times. It will then report a little bit of a report for you. So let's go ahead and bump this up to the previous example. And you can see that within a single process, this timeit module ran, and I'll change this to 5 times here. This process ran, right? And you can see that all I'm doing is creating G, I'm calling G, and sleeping for 0.05 seconds. And the neat thing is, I ran this 3 times, and in each of those 3 times, I'm actually running that 5 times. So we have a total of 15 tests, 5 occurring within the same process, and then 3 occurring within separate. And so what you can see here is I'm actually running this multiple times, and then it's taking the very best timing, which gets into a little bit of the theory, and I don't want to spoil it too much, but we have all of these different summary statistics that we can do when talking about timing or when talking about repeated measurements. Do I take the best one? Do I take the worst one? Do I take the average? Do I take the median? Do I take the 15th percentile? Because that makes just as much sense as literally everything else I just said, but we'll save that for when we get to the theory. Now, in addition to timeit, which is used for running arbitrary Python code or running entire scripts multiple times, we can also use the cprofile module. Both of these are built into Python. All cprofile is about is timing every single function call and every single function return in your program. This is very similar to the approach that I took when I showed you the set profile from sys, and this gives us a lot of information. More often than not, it gives us too much information, but I'll show you ways that we can combat that. But what you can see here is you read this just by looking. Typically, this will you can change the sort order. And so let's see if we can just do that. It's already sorted in the way that I would like it to be, but we can pass the cumulative time. This is probably the best way to pass in that. And so we'll just need this, just like that. Sleep just right there. Perfect. Okay. And so there we go. And that forces my cumulative time to be sorted. And all that's doing is saying, all right, what took the longest to run? And you have to understand that these are all going to be nested on each other. It's running built-ins.exec. That's executing my Python code. So of course it's going to take the longest. It's literally the execution of my whole program. And since it's a single module, it's all built in here. But then where we actually get to a little bit of the more interesting aspects is we can see, okay, well, I called G. And you can see that I called G just 1 time. And you can see that it's didn't really spend a lot of total time or per call time. It didn't spend a lot of time like actually executing G, but we can start to see that within G, or maybe within G, right? You can't deduce that perfectly, that this program is actually spending a lot of time calling time.sleep. And you can see that here in the total time, the per call time. So I called sleep just once, right? And on average, right, this takes 0.05 seconds. And the cumulative time that I spent is that much. And so you can see if I call G more and more, you actually see, right, my number of calls to G keeps increasing and my number of calls to sleep keeps increasing. And so that this program, right, is going to end up scaling linearly because all I'm doing is sleeping. But there are some very neat things that you can do here as long as you're willing to wade through some of the output. I'll show you what I mean by that. So we're going to keep the same things here, but now I'm going to just add an import. So we added our import and we can see just importing pandas. I can't even scroll back to the top of this because there is so much just on the import that pandas is doing. And so you can actually call cProfile in a very similar manner to what we saw with TimeIt, where I might want to be just a little bit more precise with what I'm actually trying to profile here. If I am indeed trying to profile my entire program, and I can't show you the top of this, right? Because usually we would only be interested in kind of the top here, but I'll see if I can reverse this using TAC. Very good. So now we can read this from the bottom up. It's just because my auto runner, right? I can only see so many lines, but you can see here that we're now spending 2 total seconds, right, from my built-ins. We can actually see here that a lot of this is, or some of this, right, is from Pandas import, right? That's taking about just over a second, just shy of 2 seconds, where our whole program takes 5 seconds overall. The execution of the code there takes 2. And so we can scroll down and we can see, oh, there's our G, right? There's our G and our time.sleep. It's not even the thing that takes the longest, which is absolutely crazy to me that just importing pandas takes so long, even though I've already imported it. It's already been compiled right down to bytecode. So this is quite interesting to look at. And this is why I really enjoy the cProfile. It gives you a very high level or a lot of granularity into your program. And what I like, right, since it prints out to standard out, right, we can of course just use all of our favorite shell tools. You saw me use TAC in order to reverse this, but I could do something like this, pass it to grep and do time.sleep. Let me just make sure that's what it's going to be grepped into. Yeah, looks correct to me. So I'm profiling my whole program, but now I'm only interested, right, in time.sleep or things that have lines that have time.sleep in it. You can see I can be precise with this, but do know that I'm measuring absolutely everything. The cProfile, right, is hooking into that same entry point of sys.setProfile, not at the Python level, right? This is cProfile after all. There is the exact same kind of Python API from the built-in profile module, which you can also use. It's just going to be a little bit slower.